Hey, what's up guys, this is Dr. Vivek Palipuram and I'm bringing you the next lecturette in ENGR 250 Probability and Statistics for Engineering and Computer Science. In this lecturette, I'm going to discuss independent trials. With independent trials, we are usually interested in finding probabilities of certain sequences that follow a certain property. Let's first define what independent trials are all about. Independent trials are a series of sub-experiments that are performed one after the other. In addition, each of these sub-experiments is completely independent of any other sub-experiment. So meaning that outcome of any one given sub-experiment in no way is affected by the outcomes of the other sub-experiments. For example, if I were to take a coin and if I were to flip it continuously, then that qualifies as an independent trials. The reason being, any one given flip is not at all dependent on any other flips. In addition, independent trials have one more important property, and that is each of these sub-experiments is going to have exactly same identical probability model. For example, if I were to continuously flip a coin, each coin flip has the same probability model. It's going to come up heads with certain probability, and it's going to come up tails with probability 1 minus the probability of getting a heads. If I were to perform independent trials, then probability of any one sequence with exactly n1 successes is given by 1 minus p to the n minus n1 times p to the n1. The reason being, since I have n1 successes, since I have n1 sub-experiments that are succeeding, each with probability p, if I were to multiply their probabilities, I get p to the n minus 1. P to the n1. Probability of an experiment or a sub-experiment failing is 1 minus p. Since there are n minus n1 such sub-experiments that are failing, if I were to multiply this probability 1 minus p n minus n1 times, then I get this term 1 minus p to the n minus n1. So the probability of any one given sequence with n1 successes is going to be given by this entire term. Probabilities of n0 failures and n1 successes is given by this equation right here. If you notice, this term right here is the probability that you have exactly n1 successes, or it gives you the probability of a one given sequence, exactly one sequence that has n1 successes. However, there are n choose n1 such sequences that can have n1 successes. And therefore, if you were to add the probabilities of all such sequences, each with probability given by this term, you get the answer n choose n1 times 1 minus p to the n minus n1 times p to the n1. Similarly, if I'm interested in finding out, hey, what's the probability that I have n0 failures, then that probability will be given by this term right here. Because the failure probability is 1 minus p, there are n0 failures. So I have n0 in the exponent term here. This corresponds to the successes of n minus n0 sub-experiments. This entire term is the probability of exactly one sequence that has n0 failures. However, there are n choose n0 such sequences, each with the probability given by this term. So if you were to add those n choose n0 sequences probabilities, you will get this entire term. The theory of independent trials will become much more clear if we were to solve a problem. Let's solve a problem. Let's say that I have a fair coin. You know what? Fair coin becomes a little bit too simplistic in this case. Let's say that I toss a biased coin. Let's say that I toss a biased coin that comes up heads with probability p. So it's going to come up tails with probability 1 minus p. And let's say that I toss it 10 times. First, I need to find out what's the probability that I get h for the very first flip, then t, then tails, then h, then t, then h, then t, then h, and then finally t. Notice that each of these outcomes correspond to the outcome of a given sub-experiment. Specifically, this is the outcome for experiment 1, this is the outcome for experiment 2, 3, and so on until experiment 10. So I need to find the probability of getting HT, 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 T. And this can be obtained as probability of getting the heads on the first flip times probability of getting a tails on the second flip, probability of getting heads on the third flip, probability of getting the tails on the fourth flip, probability of getting a heads on the fifth flip, probability of getting a tails on the sixth flip, then probability of getting heads on the seventh, eighth, ninth flip, and finally probability of getting a tails on the 10th flip. So probability of getting a heads is P times 1 minus P times P times 1 minus P times P times 1 minus P times P times P times P times 1 minus P. And if I were to perform this, I'll get 1 minus P to the fourth times P to the sixth. So that's a probability of exactly this sequence. Now notice that this exact sequence has 6 heads. The next question is, what is the probability that you get exactly 6 heads? In the preceding example, we found the probability of exactly one sequence that has 6 heads. Notice that how heads are placed in this sequence. Notice how 6 heads are placed in this sequence. But there are numerous other ways in which you can place 6 heads out of 10 flips. Specifically, the question then becomes, how many sequences are there that have exactly 6 heads, which can be answered by asking a question to ourselves, and that is, in how many ways can I place 6 heads in 10 flips? And that answer is 10 choose 6. So there are 10 choose 6 such sequences like the one above, each having probability equal to 1 minus P to the 4 times P to the 6, because there are 6 heads and 4 tails. So probability of getting exactly 6 heads is going to be equal to summation of those individual probabilities of 10 choose 6 sequences. So if I were to add all of those probabilities of all of those 10 choose 6 sequences, I get 10 choose 6 times 1 minus P to the 4 times P to the 6. Which is kind of the answer obtained using this particular theorem, so to speak. So the probability of getting 6 heads is 10 choose 6 times 1 minus P to the 4 times P to the 6, where 1 minus P to the 4 times P to the 6 is the probability of exactly one sequence that has 6 heads. But there are 10 choose 6 such sequences that have exactly 6 heads, each having the same probability. So if you were to add those probabilities together, you get the total probability as 10 choose 6 times 1 minus P to the 4 times P to the 6. Similarly, I can answer this question. What's the probability that I get no more than 3 heads? Probability of getting less than 3 heads can be obtained in multiple ways, and those are probability of getting 0 heads plus probability of getting 1 heads plus probability of getting 2 heads. Each of these independent trials will satisfy this condition, less than 3 heads. Now, probability of exactly one sequence that has 0 heads will be 1 minus P to the 10th times P to the 0, because I have 0 heads and I have 10 tails, and there are 10 choose 0 such sequences that have exactly 0 heads. Similarly, probability of getting 1 heads, or a sequence that has exactly 1 heads, a particular sequence with exactly 1 heads will have the probability 1 minus P to the 9th times P, and there are 10 choose 1 such sequences. Probability of an exact sequence with exactly 2 heads is going to be P squared times 1 minus P to the 8, but there are 10 choose 2 such sequences. So the total probability will be by adding all of these individual probabilities, and that will give you the probability of less than 3 heads. Now what I would like for you guys to do is, for Thursday's problem, solve this part. What is the probability that you get at least 8 heads? So when you flip a coin 10 times, what is the probability of getting at least 8 heads? Solve this problem using part B as a motivation. So use this as a motivation to solve your turn problem. The concept of independent trials can be extended to multiple states experiments. So for example, let's say that you are performing a sub-experiment where the outcomes are S0, S1, S2, and so on until S of m minus 1. Then if you were to perform several independent trials, n to be precise, then the probability of S0 appearing n0 times, S1 appearing n1 times, and Sm minus 1 appearing n of m minus 1 times is going to be given by this equation right here. Let's apply this in practice. So there are 8 virtual machines in the lab. Each computer can be in idle state I with probability 0.2, suspended state with probability 0.2, active state with probability 0.6, and independent of any other VMs. So each sub-experiment has 3 states: idle state, suspended state, and active state, where each sub-experiment is to evaluate the state of a virtual machine. What's the probability that there are equal number of idle and suspended VMs and at least 4 active VMs? Now, since there are 8 virtual machines, I need to find what is the probability that there are equal number of idle and suspended VMs and at least 4 active VMs. So I need to find what is the probability that idle is equal to suspended and active number of active VMs is greater than or equal to 4. Now this can happen as follows. I can have exactly 4 active VMs, and suspended VMs and idle VMs have to be equal, so they will be 2 each. If I were to have 5 active VMs, then I cannot have equal number of suspended and idle VMs, because I cannot split 3 virtual machines into equal parts between idle and suspended, because your virtual machines will be either idle or suspended. So active VMs equal to 5 cannot happen. But I can have 6 active VMs and equal number of suspended VMs, 1 each. Equal number of idle and suspended VMs, 1 each. I can also have 8 active VMs and equal number of idle and suspended VMs, which is 0 each. So I need to find the probabilities of these terms. So I'll apply this formula right here to evaluate these individual terms. So to get the first term, I have 8 choose 4, 2, 2. Probability of an active VM is 0.6, so 0.6 to the 4. Probability of an idle VM is 0.2, so 0.2 squared, 0.2 squared for the suspended, plus for this term, I will have 8 choose 6, 1, 1. Probability of an active VM is 0.6, so 0.6 to the 6 times 0.2 to the 1, 0.2 to the 1. And for the last term here, I have 8 choose 8, 0, 0. Probability of an active VM is 0.6, so 0.6 to the 8 times 0.2 to the 0 times 0.2 to the 0. So if I were to add these individual probabilities, I'll get the probability that there are equal number of idle and suspended VMs and at least 4 active VMs. All right, so that brings us to the end of this lecture video where I discussed independent trials. For our class on Thursday, I'll go through some more problems with respect to independent trials so that this concept becomes much more clear. I think it's a good time to stop this lecturette right here. And also with this lecturette, I would say that we have come to a conclusion of basic probability theory phase of phase 1. Next, we are going to look into some advanced probability theory concepts, which includes the usage of random variables. And that's an agenda for the next week. Thank you for listening.